So remember before I told you about how you can compute the determinant of a matrix with integer entries by solving ax equal to v, and then looking at for a random choice of a vector v, then looking at the vector x you get, and by Cramer's rule, the denominators of the vector x are very close approximations. They're divisors of the actual determinant. Because Cramer's rule gives a formula for a solution of ax equal to v, and it involves the determinant of a everywhere in the denominator, and various other things in the numerators. And you don't actually want to use it, it's a horrible formula, but it tells you theoretically that the only thing you're going to see in the denominator is a bunch of determinants. Or rather, the only thing you're going to see in the denominator of this vector, if v has integer entries and a has integer entries, are divisors of the determinant of a. And if things are sufficiently random, maybe you'll just get the determinant of a. Or if you don't, you'll get something very close, and with a little additional work I didn't talk about, you can get the determinant of a. And just to give you a sense of speed, for a 1,000 by 1,000 matrix whose entries are between minus 10 and 10, it takes about 10 seconds to compute the determinant, which is pretty fast if you think about it. That's a matrix with 1 million entries, and these are exact numbers. And this determinant that came out, if you look at the length of the string, is over 2,000 digits. So, by hand, you would never compute the determinant of a 1,000 by 1,000 matrix in 10 seconds. You couldn't even write it down, and it'd probably take you an hour just to write it down. Also, clearly, this is not using the algorithm that you're implementing in your homework, right? Because that would take 1,000 factorial steps at least. And 1,000 factorial is really big. Yes?
So the determinant A was cached?
Yes. So, oh man. Oh well. Didn't mess up the screencast. Will it come back? Yes. All right, that'll keep you on your toes. So watch, if you do time at a.det, it will always seem very fast. Very, very fast. Why? Because, see, it says 143 nanoseconds, because it caches the result. If you do a.clear cache, I think, then just time it. Then I think that will really take the full 10 seconds, at least. So you can also change one entry of the matrix. Wow, why is that happening? So another thing you could do would be to just change an entry of the matrix. I'll just change the 0, 0 entry to be 5. And anytime you change an entry of the matrix, it clears all this stuff it's cached about the matrix. Obviously, because the determinant will have changed. Okay, so that's that. I just wanted to remind you of that. So here's another central idea in exact linear algebra. It's something called multimodular echelon form. And it illustrates, it's a special, come on. Obviously, it's not failing to save, because look. It illustrates a general class of algorithms, and if you understand this one, you can apply it in a lot of different contexts, not just matrices and so on. So here's our sample matrix. It's a random 4 by 5 matrix. Those are the entries, but it's a random matrix. I didn't make this up specifically so that you're in Math 308, and when you do the echelon form, every step of the way comes out beautifully, right? It's really just the only thing that's not random is I set the seed to a very important number, 42. So other than that, it's just a random matrix. It's not going to have a pretty echelon form. Also, it's not a square matrix. If you take a random square matrix, the echelon form is what? What is the reduced row echelon form of a random square matrix? Yep, it's just the identity matrix. Because a random matrix is invertible, and when you put it in reduced row echelon form, at every step you end up being able to, well, I'm not going to justify that because that's a different class.
Sorry, why is the random matrix invertible?
Okay. What is the rank of a random matrix?
I don't know what we mean.
Okay, so
matrix.
A matrix has full rank, it's invertible, if and only if its determinant is non-zero. So imagine all n by n matrices. That's an n squared dimensional space. The determinant condition, the condition that the determinant is equal to 0, cuts out a surface, a hypersurface, in an n squared dimensional space. A random matrix is like a point in that n squared dimensional space. What are the odds that a randomly chosen point in an n squared dimensional space lies on some surface in it? 0. So a very special case. If I drew a surface in this room, and then you just chose a random point, what are the odds it lies on that surface? Vanishingly small. So the odds that a randomly chosen matrix has determinant 0 is similarly vanishingly small, because determinant equals 0 is a condition that geometrically just cuts out a surface inside of your high dimensional space of all matrices. Right? No, I don't know.
Okay, that makes sense.
Or another way is, in order for the matrix to not have full rank, you have to have some row as a linear combination of previous rows. And if you take the span of all the previous rows up to the row you're looking at, that's some subspace of your whole vector space. And if you imagine a vector space, that's like a big square thing. A subspace is like a plane or a line or something in there. So it's highly unlikely that some new randomly chosen point lives in a subspace. So if you're making a matrix at random by adding rows at random to a matrix, you're with 100%, with super high probability, always going to get something that's not in the span of what you had already. And hence, randomly chosen matrices have full rank. Oh, that's an error about saving the read-only assignment. Okay, that's probably what you caused and reported. It's now sitting there trying to save your edits to a read-only file, which of course is failing because I had it opened. Okay. So that's why. All right, so let's take this matrix and imagine we're in Math 308 and our instructor has told us to put this in reduced row echelon form. Okay, so what you would do is you would take the first row. Okay, I kind of did it wrong here in the first, but you'll see. You take the first row and use it to clear the first column. And then you take the next row and you rescale it so the leading entry is 1, and then you clear the second column, the third column, etc. So let's just do that. So I just defined my matrix, and now I guess I need to split the screen so we can see two things at the same time. So I'm going to put the matrix over here so that you can see it while we echelonize. So I don't know why. I just started adding multiples of one row to another, which is, oh, it's never going to work. Look. I just started adding, so I added minus 3/9 times the first row to the second row, and that cleared that row. So let's just do that, and that ends up with the row. Well, what I've done to make it easier is I've just done it by reprinting the matrix each time. So I forgot that I should clear the first row and make the leading coefficient 1. I just didn't do that. I'll do that at the end. It's equivalent. So I'm just going to add now minus 8/9 times row 0 to row 2, and then show you what I get. And there we are. See, I'm just clearing the rows. And now I'll add 6/9 times row 0 to row 3, and this is what I get. Okay? So I'm doing the standard Gauss elimination algorithm. The point I want to make is just that the numbers are starting to look ugly and painful. So, hey, thanks, John. And so we just rescale the first entry to be 1. Okay, so that's the first sort of clearing of the first column. And let's just keep doing that. Let's take the second column. So I've now rescaled the second row, so it starts with a 1, and now I clear the second column. It's very important to do this in order, because we're mutating A as we go. See? So again, if you were doing this in an exam on paper, how would you feel at this point? Like, you're terrified, you're sure you're wrong. Like, there's no possible way you aren't wrong. But even if, like, what if, like, halfway through the exam it actually told you you're right? Like, it puts that right there, and you're like, oh, you were actually right. Then you're like, oh my God, this is going to be a lot of work, and I'm only halfway through. And, like, it's just going to get worse and worse, right? These numbers are going to get huge. The point is just that imagine doing this on a 200 by 201 matrix. So a really big matrix with, like, hundreds of rows and columns. Every time you do this, the numbers are just going to start growing and growing and growing, and it's really going to get out of control. So this algorithm, though it will work, it is painful because all inside of your matrix, you get all these big numbers. But look what happens. If you keep doing this at the end, here's what it looks like. Except for the very last column, it's a really simple, nice little matrix. It's the identity matrix. In fact, for any random n by n plus 1 matrix, it's going to look like this. You're going to have the identity matrix, and then some final column with big numbers in it. Of course, there are special matrices where that doesn't happen, but for a random one, that is what will happen. So it's kind of disturbing that you do all this work along the way with these huge numbers, and then you just they all go away at the end. Wouldn't it be nice to just get directly to this and that, somehow without all the big numbers in the middle? So that's what motivates this idea of multimodular algorithms. So basically, there's a better approach to computing the reduced row echelon form of a matrix over the rationals, and it completely avoids this coefficient explosion. You never do arithmetic with fractions and they keep getting bigger and bigger. And it also enables a whole bunch of ideas and optimizations. What we're going to do instead is take our matrix and reduce it modulo a prime number p. And then do exactly what we were doing before, but always working modulo that prime number p. That's really nice because there are no fractions involved. I'm assuming that you understand arithmetic modulo p, which is you add two numbers and you divide by p and take the remainder. That's addition mod p. And multiplication mod p, you just multiply the two numbers, divide by p and take the remainder. And you get a field. Remember I mentioned fields before. A collection of numbers that you can add and multiply. And also divide. Any non-zero number mod p, there's something you can multiply by it to get 1. And if 12 were a prime, working with a clock, like 5 o'clock plus 9 o'clock, what time is that? 5 plus 9, mod 12. It's 14 o'clock, but 14 mod 12 is 2. So if you say 9 o'clock, or if you say 5 o'clock, what time is it 9 hours later? It's 2 o'clock. You've just done addition modulo 12. And here I'm talking about addition and multiplication modulo some chosen prime number p. The point is you never ever have any fractions, and the numbers don't explode in size. No matter how many multiplies and adds you do, the numbers are always between 0 and p minus 1. Okay, so you choose a random prime number p, you reduce the matrix modulo p, you just do the whole reduced row echelon form algorithm exactly like normal, modulo p, and then you lift the result back up to the rational numbers. So let's give it a shot. So I'll take our matrix as before. And there's our matrix, and here we've reduced it modulo p in the bottom. So all the negative numbers, so the numbers modulo p in stage at least are represented as integers between 0 and p minus 1. In particular, a negative number, such as minus 9, since we're working modulo my favorite prime number, 389, minus 9 is represented as 380. Yes?
Why is it your favorite prime number?
Because it's the only known prime number p that divides the discriminant of the Heck algebra associated to weight 2 cuspidal modular forms of level p.
Oh, well, of course.
Which plays a key role in Ken Rubin's application of the Manin-Mumford conjecture to finding rational points on modular curves. So there you are. In other words, it's complicated. My relationship status to 389 is complicated. So there you are. That's this matrix, but modulo 389. And now we're just going to take this matrix right here and compute its reduced row echelon form. And here, everything works exactly like in 308. You can rescale the first row, which is what I should have done before. So when I say divide by 380, you do the division in the field of numbers modulo p. So you find some other number mod 389 such that the product of it with 380 is equal to 1, and then you multiply that row through by that. And you end up with something that starts with a 1, and now you add minus 386 times the first row to the second row, and you get this. So notice, for example, that 138, you get that by computing minus 386 times 44 and adding that to 6. And you get some big integer, but then you reduce it mod 389. You divide it by 389 and take the remainder. In other words, minus 386 times 44 plus 6, I'm computing that 138 there, is that number. But if you take that number right there and reduce it mod 389, you get 138. See?
Where did you write, it looks like you just knew to do the mod 389.
Yes, it's because B, if we go back to where it was defined, B,
Okay.
I get that by taking my original matrix and reducing it mod 389. Okay. This change ring thing is important. The matrix is over Q. If I directly reduce this matrix mod 389, I just get the 0 matrix, because the ideal generated by 389 in the field Q is the unit ideal, which means nothing if you don't know some commutative algebra. But if you change it to Z, then it all works fine. Okay. Okay, and then we're just going to do it. We clear the first column. The key thing to watch here as this happens is that, and now we're clearing the second column. This is less disturbing than what we saw above. Yes?
So you could mod by like ideals generated by arbitrary
Yep.
generators?
Yep. Yep. And if you were going to, say, consider echelon forms of matrices whose entries are in a rational function field, so all rational functions, so quotients of polynomials, then the same algorithm works. But instead, you reduce modulo an irreducible polynomial. So the point is that the numbers are not getting big. Isn't that great? So the numbers, they stay kind of bounded in size. They stay between 0 and 3, 8 inclusive. And as you go, you end up with that as the reduced echelon form. The numbers do not explode in size. Even if our original matrix were 200 by 201, if it had hundreds and hundreds of rows and columns, if you do the Gauss elimination algorithm mod 389, the numbers are never going to get big because they always get reduced mod 389. And there are a lot of other advantages. And here's what you get. So now the final step would be to go from this echelon form back to our echelon form over Q. Unfortunately, there's kind of a wrinkle here. So here's what the echelon form of the original matrix looks like. And somehow we're supposed to go from that one up there at the top to the one at the bottom. And you might be suspicious because there just might not be enough information encoded in the matrix at the top. I chose 389 because it was my favorite prime. I could have done this whole algorithm and chosen the prime to be, 2 or 3. And there's just no way that doing everything modulo 2 or 3 is going to be enough information to get those big rational numbers on the right-hand side, right? You understand? There isn't enough information there. If you chose the prime sufficiently large, then there might be, but even then it's kind of subtle because those are fractions, whereas those are numbers mod p. How can you get from numbers mod p to fractions in a natural way? Like you could take numbers mod p and lift them to integers, but you don't get fractions when you do that. And so this puzzled me a lot when I was learning about this, but there is actually a clever way to do that, to lift and get rational numbers. Okay, so just to summarize what I said, there's not enough information in this. So if you take, say, the upper right entry, it's that fraction, minus 3231 over 1600. If you reduce it mod 389, you do get 236. It's consistent with the calculation we did. What do I mean by reducing a rational number mod a prime? That's something you almost certainly won't even learn about when you take Of course, it involves reducing mod primes. What I mean is you take the denominator and you find some number mod p that's the inverse of 1600 mod p, and then you multiply that by minus 3231. So that's how this is defined. This would not make any sense if the denominator were divisible by 389. So usually this will work in the following sense. When you, and not always, but usually, if you take the echelon form, if you take your original matrix, reduce it mod p, compute the echelon form, and compare that to the reduction mod p of the echelon form that you're looking for, it's usually the case that they'll be equal. But not always. You could get very unlucky and choose a bad prime p. Like, what if you chose 2? Then it's pretty unlikely that's going to work because you can't even reduce these modulo 2. Things are just going to go really bad mod 2. Just to maybe convince you of that, look what happens if we were to do this echelon thing but mod 2. Then it will just completely break. And for some big crazy matrix, maybe some other numbers fail. Okay, look at that. So that, I mean, it doesn't even look, there's no way that if you reduce the bottom one mod 2, you're getting the top one. Because it doesn't even make sense to reduce the bottom one mod 2 because of these denominators. But even if it did, I mean, it's just, even the shape is wrong. There's just no way it's going to work. So if you can figure out how to, so there's a couple of problems to solve, but the basic idea is there. If you can figure out which primes to avoid, and you can figure out how to compute the reduced row echelon form quickly mod p, and you can do it for several different primes, combine together the answer, and then lift that to rational numbers, and you can figure out whether you worked modulo enough different primes, then this works. And it will give you a way of computing echelon forms. So let me add that. First, there's an algorithm called rational reconstruction. And what this does is it lets you take a number modulo a prime or even modulo a composite, and then find if there's a rational number whose numerator and denominator in digits are about half as many digits as this prime, it will find that rational number. And it will be uniquely determined. Otherwise, it will tell you there is no such rational number. So the idea, again, is you take your original matrix, you reduce it mod maybe 20 different primes, all fairly small. You compute the reduced row echelon form modulo all of those primes. Then you use the Chinese remainder theorem to combine together all of those echelon forms into one big matrix, and then you use this rational reconstruction function, which is based on the Euclidean GCD, to find the unique rational number, the unique matrix of rational numbers that reduces to the matrix that you found using the Chinese remainder theorem. And there are so many places in that algorithm that you can make things really, really fast. Because, first, all the arithmetic that you do is just arithmetic mod a bunch of small primes. So you can do it mod all the primes at once in parallel. That's really fast. Second, because you're always working modulo small primes, you can use ints or longs. It's like machine size numbers. You never have to do like arithmetic with arbitrarily large numbers. You get to like use the int data type or the long data type, which is often like 100 times faster than using bigger numbers. So that's really good. And moreover, one other thing is the echelon form, computing echelon forms modulo, well, I just want to show you a few more examples, but computing echelon forms modulo primes can be made very fast. And why is that? Suppose you have a matrix and you want to compute its echelon form. Here's another trick that is really useful. You can reduce it to matrix multiplication. Doesn't that sound completely insane? I claim that computing the reduced row echelon form of a matrix in complexity is the same as computing matrix multiplications, which surprisingly can be done very quickly due to subtle observation of Strawson. That's very surprising because they look like two very, very different problems. However, imagine you take your matrix that you want to compute the reduced row echelon form of. Let's say it's this 500 by 500 random matrix that I'm about to define over the rational numbers. So I just defined a terrifying 500 by 501 actually matrix. Now imagine taking that matrix and just breaking it up into it has 500 rows, but just break it up into maybe the first 300 rows and 200 more rows, and then break it up vertically as well. And so now you have a 2 by 2 matrix of submatrices. And kind of just forget about the fact that they're not quite square, and just make them square. And maybe forget about the fact that they might not all be invertible, and maybe permute things around so that they are invertible, and keep track of what you did. Then you can reduce the problem of echelon form of the huge matrix to echelon form of a 2 by 2 matrix whose entries are matrices. And then you use the normal Gauss elimination algorithm, but on that little 2 by 2 matrix of matrices. But what do you have to do in order to do Gauss elimination? You have to multiply it through a row to make the upper left entry a 1. And that's exactly a matrix multiplication operation. So if matrix multiplication just happened to be shockingly fast, then you could actually do echelon forms very quickly, as long as you're very clever. And I'll tell you, it is really hard to implement that algorithm properly without bugs, but it's possible. But just the issues of keeping track of permuting the columns and rows to make things invertible, it's very, very painful, but it can be done. It has been done. And it leads to doing echelon forms entirely by doing matrix multiplications. And one of the big surprises in linear algebra is that most algorithms can be reduced to matrix multiplication. And the motivation for that is that matrix multiplication is way faster than O of n cubed, as it turns out. We don't actually know, it's an unsolved problem, what the best algorithm is for matrix multiplication. We don't know how fast it is, but it's definitely faster than O of n cubed. There's a link to a Wikipedia page here about this.
Is n like the dimension?
Yeah. So if you have an
n squared?
if you have an n by n matrix, then the naive algorithm for matrix multiplication, the one that you learn in the definition of matrix multiplication, requires n cubed multiplications. But it turns out that you can do it using far less than n cubed multiplications. That's Straussen's idea. So Straussen gives you O of n to the log base 2 of 7, and then Vinogradov and other people give you even better complexity. But it's an open problem to know what the best complexity is. Okay, so let's see how long it takes for a 500 by 501 matrix to compute its echelon form. It takes less time than it takes to announce that I'm going to do it. So it takes a little over a second. And here's what the answer looks like. That's one entry of the answer. It's very big. And internally, under the hood, it wasn't doing an enormous number of calculations that use lots of memory with rational numbers. It did a lot of calculations mod p, and then it recovered this rational solution. Okay, so done telling you all about linear algebra. The pattern of that algorithm, though, is very general. It gets used in a lot of other contexts. Okay, so the next thing I hope we can do for 2 or 3 minutes is just stress test this. So I have a worksheet. I hope that some other people can open it. If you're in the shared project and you click log, you'll see that it's being opened by people right now, and therefore you can follow it. Let's see how long it takes until everything goes to hell. This is very colorful. In particular, let's see if we can get it all corrupted. So far, it's not all messed up. Nobody's really done much of anything. Oh, okay. I want to do something. Come on. Ha! Seems like a lot of people are evaluating things.
Is this in the shared project?
Yes, it's in the shared project. Let's see if the CPU 100, 99. So it's definitely using a lot of CPU. Somebody wants to draw a sphere cube. Where's everybody's faces? Does anybody else see faces for everybody? That has nothing to do with this. Hey, somebody successfully drew a plot. Woohoo! I'm going to change it. does not look good. All right. Here come that boy. Dare I open time travel? So, wow. So 286 revisions in about how long? In 1 minute. Already made almost 300 revisions. Jeez. All right. I think it's all over. No? So it doesn't look like it's all corrupted for me. I'm not seeing any corruption, like funny characters or anything. I haven't implemented any sort of rate limiting when there's multiple people. Like one individual person can only like make changes about once per second or so, but I don't have it set up where if there are 30 people at once, it's still at most 1 per second. And that's why the number of revisions is growing, so quickly, 370 in about 1 minute. And that's why your CPU usage just goes crazy. And I will implement that next. But okay, how many people's laptops are just frozen as a result of this? I don't see any hands. Does yours is, okay. Mine's actually not. So it's kind of progress over last time, right? Does anybody else have any faces? I have no faces. Sure.
Yes.
Okay, I guess it's just me. All right, well, there we are. So, hey. Okay, well, that was useful. So, work on your homework. I will walk around, and then I'll also sit outside over there if we get kicked out of here for like 15 minutes to answer additional questions. Okay? And let me stop this screen cap.